Particles of gravity. Well, that sounds like a strange concept. And gravity in general is a strange thing. On the one hand, of the four fundamental interactions, gravity, electromagnetism, and the weak and the strong nuclear forces, the effects of gravity are probably the most intuitive. I let it go, it falls. The larger mass, the Earth, attracts the smaller mass. On the other hand, it is gravity that is the stumbling block in building this so-called theory of everything. The three other interactions fit quite well within the framework of quantum theory, whereas gravity stands apart. Even though we understand from everyday experience what gravity does, it's not easy to imagine where any hypothetical gravity particles would fit into this picture. To a non-specialist, it may be completely unclear why they would be needed at all. That's exactly what we're going to try to figure out today. Let's talk about quantum gravity and gravitons, the quanta of gravity. Do they exist? What should they be like? Can they be detected? What experiments already exist in this field? And what does all of this even mean? I'm Andrei, and this is Cosmos Elementary. Gravitons are probably the most elusive particles, but why should gravity even have particles at all? And in fact, they don't have to. Nevertheless, many scientists today believe that they may exist, and there are quite a few interesting arguments in support of that idea. For now, however, gravitons remain purely hypothetical particles. We have no direct evidence that they exist. Scientists have also been debating for decades whether it's even possible in principle to detect them. However, there have been some interesting experiments in recent years, and we will talk about them later today. And what is the logic behind all this? So, we have four fundamental interactions, which are also called the four forces of nature or of the universe. And they, in a way, govern all the processes we observe in the universe. I talked about them in some detail recently in videos about hypothetical fifth force and the grand unified theory. Three of the four forces, electromagnetism, the weak interaction, and the strong interaction, are described by the standard model of elementary particles. And the key point is that each of them has its own particle, or a set of carrier particles or gauge bosons. The photon for electromagnetism, W and Z bosons for the weak interaction, and a group of gluons for the strong interaction. There are 8 of them in total. These particles are the mechanism through which interactions operate. Why do particles with the same electric charge, for example 2 electrons, repel each other while opposite charges attract? How do they know they're supposed to do that? These particles are the carriers of interactions, in this case photons. Electrons exchange them, and this leads to a specific result. Similarly, quarks inside a proton or neutron exchange gluons, which is what holds them together. As I said earlier, such force-carrying particles have only been identified for 3 of the 4 interactions, but for gravity they have not. The graviton is essentially the missing, hypothetical force-carrying particle of gravity, and another way of describing the gravitational interaction in which objects with mass attract each other by exchanging these particles. At first glance, it seems logical that since all other forces have these particles, gravity should have them too. But in reality, this is not necessarily the case. It is entirely possible that gravity is fundamentally different from other interactions. What is the problem today, and why does a complete quantum theory of gravity still not exist? If you look at how gravity differs from other fundamental interactions or forces, it might seem not so surprising that it still can't be unified with them, and that we still haven't managed to build the so-called theory of everything. Interestingly, it is gravity that most often excites the imagination of conspiracy theorists. Then they say that gravity is actually electromagnetism. But here they somehow fail to explain why the Earth attracts objects equally regardless of their charge, whether they are charged or neutral. A magnet and a piece of wood both fall to the ground in exactly the same way. Others even claim that gravity does not exist at all, and so on. But I've never really heard conspiracy theories about, for instance, the strong nuclear interaction. As I said, gravity is unique. But in reality, it is quite different. And it is precisely because of some of these differences that it is so difficult to unify gravity with the other forces and build the so-called theory of everything. I've already mentioned some of these differences before. For example, gravity is the weakest of all fundamental interactions. And it is not just slightly weaker, it is weaker by many orders of magnitude. A classical example is when a weak magnet can overcome the gravity of the entire planet. It might seem that it's not such a fundamental problem. Okay, it is weaker, so what? But here's another example. Electromagnetism, the strong and weak interactions, act on particles that possess a certain kind of charge. I'm using the word charge here in a general sense. With electromagnetism, it's pretty straightforward. Particles affected by strong interaction have what is called a color charge. Of course, this has nothing to do with color in the usual sense of the word. Electromagnetism has two types of charge, negative and positive. The strong interaction has three. Gravity has no positive or negative charges, and no different colors. It has only one kind of charge, which is mass energy. And this leads to an interesting conclusion. If other interactions affect only those particles that carry the relevant charges, then gravity affects everything that has energy or mass. In other words, everything. It is the only force that acts on all particles, and in fact on everything around us. Photons have no mass, but they do have energy, and they also distort space. Light follows trajectories in space-time that is curved by mass. In other words, it is also affected by gravity. And here's another important difference. As we know, the modern theory of gravity is Einstein's general relativity, in which unified space-time is not just an empty void, but a physical entity in its own right that in the presence of mass or energy becomes curved. And objects that curve space-time cause other objects to move along that curved space-time in a specific way. That is what we call gravity. And this is the reason why you might sometimes hear that gravity is not a force in the usual sense at all. But for now, this is not so important. So the theories of other three forces, electromagnetism and the weak and the strong interactions, describe them as something that happens against the backdrop of a fixed space-time. And only the theory of gravity describes the evolution of space-time itself. In other words, the three other forces occur within space-time, while gravity is an effect of space-time itself. And since we're already talking about theories, the theory of gravity, general relativity, is classical. Classical does not mean old, it means non-quantum. Often when describing the difference between general relativity and quantum theories, the emphasis is placed on the fact that gravitational theory describes what happens on macroscopic scales, on scales of humans, planets, stars, and galaxies. Quantum theories describe what happens on microscopic scales or subatomic scales. This is the world of electrons, quarks, and so on. In a classical theory, physical quantities always have well-defined values that we can in principle measure with great precision. For example, an airplane is flying and we can determine its exact speed and position. In quantum theories, however, doing the same for particles is not possible. According to the uncertainty principle, it is impossible to know absolutely everything about a particle with perfect precision. For instance, the more precisely we measure a particle's velocity, the less precisely we know its position, and vice versa. The same applies to other pairs of parameters as well. In classical theory, nothing of this sort exists. This is related to the fact that classical theory is deterministic. If we know everything about the current state of a system, then we can precisely predict what will happen to it in the future. If we throw a ball and take a snapshot, knowing its current position, velocity, direction, and all the factors that can affect it, we can precisely predict the trajectory along which the ball will continue to move and where it will end up. This line of reasoning is sometimes taken to rather extraordinary conclusions that everything in the world is predetermined and that we have no free will. I've already made a separate video about that. In quantum theories, on the other hand, everything is governed by probabilities. As I've already said, we cannot determine the exact initial state of a system with perfect accuracy. And therefore, we also cannot precisely predict what will happen to it. We can only talk about certain probabilities of what may happen to the system. And there is another especially important difference for us today. In quantum mechanics, physical quantities are quantized. This means that energy, position, momentum, spin, and so on cannot take arbitrary values, only specific ones. Let's take energy as an example. In classical mechanics, the possible energy levels can be represented as a smooth, continuous slope, where you can stop at any point. From the perspective of quantum mechanics, instead of a slope, there is what would look like a staircase where each step represents a specific energy level. In the classical version, you can stop at values like 3.46 or 4.2, but in the quantum case, only certain levels are allowed, say 2, 3, 4, and so on. This is reflected in the table of the standard model of elementary particles, where, for example, charge values are not arbitrary, but either integer multipliers or specific fractions of the elementary electric charge. Similarly, spin is not arbitrary either. For quarks and leptons it equals 1/2, while for force carrier particles it equals 1. A clear example of this is the fact that electrons in atoms occupy strictly defined energy levels. The diversity of chemical elements depends on this. And for an electron to jump to another energy level, it is not enough to simply supply a lot of energy. It requires radiation with a specific wavelength. In other words, it's not the amount of light that matters, but the type of light. Then, after some time, the electron loses the energy it gained and emits the light back. Thanks to this property, spectroscopy works and allows us to determine the chemical composition of substances both in the laboratory and of distant cosmic objects, simply by studying their spectrum. And now we also need to remember that the main modern quantum theories describing 3 out of 4 fundamental forces are quantum field theories, such as quantum electrodynamics for the electromagnetic interaction or quantum chromodynamics for the strong interaction. At the center of them are quantum fields that permeate the entire universe, and particles are excitations of these fields with a certain amount of energy. In the case of gravity, we also use the word field, a gravitational field. However, the difference is that this field is classical rather than quantum. It is not quantized. It is smooth and continuous, so to speak. The grid here is used only for visualization. And quantum fields have their own discrete quanta. A photon is the quantum of the electromagnetic field. Gluons are the quanta of the gluon field, and so on. General relativity is not a quantum theory, which is why it does not contain any particles of gravity. The graviton, in turn, would be the quantum of the gravitational field in a quantum theory of gravity, if we had one. More precisely, there are several attempts to build such a theory, including ones you have probably heard of, such as string theory, as well as others. So what exactly is the problem with constructing a quantum theory of gravity? I've already mentioned some of the ways in which gravity differs from the other forces. But if we look at other forces, for example, electromagnetism, it was also originally described by classical theory, and only later was quantum electrodynamics developed. Perhaps we could just take similar mathematical methods and apply them to gravity, quantize it, so to speak, and be done with it. In fact, that's exactly what physicists tried to do for a long time. But it didn't work. And here's why. When scientists try to build a quantum description of fundamental interactions, infinities start appearing in the calculations. Physicists don't like infinities because they usually signal that something is wrong with the theory. But there is a way to deal with these infinities. This is where a so-called renormalization is used. We will not go into details here, but in short, the idea is that additional parameters are introduced into calculations in a specific way, which cancel out these infinities. It sounds like a mathematical trick, and in a sense, that's exactly what it is. But this trick leads to a situation where the theory not only produces results that make physical sense, but also matches experimental data with extremely high precision. Theories for which this method works are renormalizable theories. The quantum theories that describe 3 of the 4 interactions are like that. But when we try to construct quantum gravity in a similar way, it turns out to be non-renormalizable. What does that mean? And when we try to quantize gravity, infinities also appear. But unlike other cases, renormalization does not work here, because in order to remove one set of infinities, we are forced to introduce an infinite number of additional parameters. This is often one of the things people mean when they say that general relativity cannot be reconciled with quantum gravity. Still, scientists have not given up on the search for quantum theory of gravity. Too much is at stake here. And the possibility of solving problems related to black holes, for example the problem of singularities, understanding what happens in the first moments of the universe existence, something our current theories still cannot fully handle, and of course to create the long-sought theory of everything. Among other approaches to quantum gravity are various versions of string theory, or the more recent version M-theory, and also loop quantum gravity, which we will come back to later today. At the same time, one cannot rule out the possibility that gravity may not be quantizable. In other words, it could be fundamentally different and operate in a different way than other interactions. And there are some scientists who adhere to this point of view. In that case, there are no gravitons at all. And conversely, if we manage to find a graviton, it would prove the quantum nature of gravity. Interestingly, scientists even have some ideas about what this graviton might be like. As with many still hypothetical things, there isn't just one description of graviton, although in general many physicists agree on fairly specific properties. But for us, non-specialists, what may be confusing at first is simply what is a graviton at all? How can gravity even have a particle? And yes, this is probably not the most intuitive idea, but here we can draw a parallel with other particles and fields. Taking electromagnetism as an example for which a quantum description already exists. We have two charged particles, say electrons, which can also be described as excitations in the electron field with a certain energy. When they get close enough, they repel each other. And modern theories explain this by saying that two electrons have exchanged a photon, the force carrier of the electromagnetic interaction, which is an excitation in the electromagnetic field, also called the photon field. In the case of gravitons, the situation is similar, only instead of electrons, which must have a specific charge, we can consider any particles with mass or energy. And when they get close enough, they attract each other through gravity by exchanging gravitons, which are excitations of the gravitational field. So in this picture, it is not that the fabric of space-time itself is made of tiny particles. That idea is more associated with loop quantum gravity. Another important detail I left out in the previous comparison, electrons don't exchange just any photons, but virtual ones. Many people find this term confusing. What are virtual particles supposed to be? And people often debate whether they even exist at all. And yes, I have made a separate video about virtual particles. It's worth remembering that in many ways the word virtual itself gets in the way here. It is in a sense just an unfortunate label. The calculations that describe particle interactions using virtual particles not only work on paper, but are also strongly confirmed by experiments. However, since we cannot see or, so to speak, touch these particles, some people refer to them simply as a convenient mathematical tool. There's also another way to describe virtual particles. For this, we again need to look at particles as excitations in fields. Recall that according to quantum field theory, every particle corresponds to its own field, and these fields permeate the entire universe. That means that at every point in the universe there are fields, and even if there is no particle in the usual sense at that point, these fields still have certain minimum values. And it's also very important that these fields can interact with each other, and the interaction between two electrons can be described as follows. Two electrons, two excitations in the electron field approach each other, and when they get close enough, having a certain charge, they begin to interact with another field, electromagnetic or photon field. This interaction in turn creates a disturbance in the electromagnetic field, and that disturbance is what becomes the so-called virtual photon that, quote-unquote, pushes the two electrons apart. In this description, even the word exchange doesn't really work. The disturbance in the photon field is quite real, but it's called virtual because it does not exist independently. It appears only when the electrons approach each other, and as they move apart, it disappears again. This is what distinguishes it from a quote-unquote real photon, which exists on its own. And coming back to gravitons as force-carrying particles of the gravitational interaction, they would work in a similar way. Particles with mass energy would create disturbances in the gravitational field. Actually, even electrons themselves, which do have mass, are also affected by gravity. Although, as we remember, that is much weaker than the electromagnetic interaction. By the way, the comparison between gravitons and photons is not accidental. Modern theories predict that if gravitons exist, they should have certain properties. And in some respects, the graviton is similar to the photon. Most likely, they, like photons, have no mass. And therefore, like photons, they move at the speed of light. Gravitons differ in spin. If they exist, it would be the only elementary particle with spin 2. But as we know, gravitons have not yet been directly detected, but could they manifest themselves in some way? There is another interesting aspect in comparing gravitons with photons. Photons are not only carriers of electromagnetic interaction, they are not always virtual. We can also observe them directly, which is what allows you to watch this video right now. Of course, I'm talking about light, both visible light and electromagnetic radiation in general. Light has a quantum nature and consists of photons, which, like essentially all other particles, can behave both like particles and like waves. Do you see where I'm going with this? Of course, gravitational waves, which, unlike hypothetical individual particles such as gravitons, have in fact been directly experimentally detected. Gravitational waves in the fabric of space-time can in principle be generated by almost anything, even say the motion of my hand. But such waves would be extremely weak. The gravitational waves we can currently detect are triggered by extreme events, such as the merger of black holes or neutron stars. Astrophysicist and science communicator Ethan Siegel compares gravitational waves to waves on water. We see waves on water with our own eyes. They are macroscopic objects. But if we zoom in enough, we find that they're actually the collective motion of a large number of water molecules. The situation with gravitational waves may be similar. And the difference for now is that we can observe macroscopic objects using detectors, whereas gravitons at microscopic scales have not yet been found. A similar story holds for light. We see light waves with our eyes, and modern laboratory equipment is capable of detecting and counting individual photons. But with gravitons, things are still difficult for now. And the properties of gravitational waves also match the predicted properties of gravitons. In particular, according to our most precise modern measurements of gravitational wave events, they propagate at the speed of light, or very close to the speed of light. Very close because there can be still measurement uncertainties in the data. If, for example, we measured that a gravitational signal from a merger event arrived much later than the light signal, and we concluded that it travels much slower than light, that would already not fit very well with the concept of gravitons. And again, since the waves propagate at the speed of light, it means that the corresponding particles are massless, which matches the predictions. But we're still looking at gravity through the lens of classical physics, and in order to prove its quantum nature, it would be useful to detect not only waves, but also individual particles, similar to how scientists detect single photons. Indeed, scientists are not even sure whether this is possible in principle, and this is not least because gravity is so much weaker than all other interactions. In earlier considerations, scientists concluded that a detector capable of registering a graviton would have to have such properties that it would itself collapse into a black hole. More recent estimates are somewhat more optimistic. For example, the authors of such a paper estimated that gravitons could be directly detected only if one builds a detector with the mass of Jupiter and places it near a neutron star. Even then, it would at best register a single graviton over the course of several years. And even in that case, it would be extremely difficult to distinguish a graviton signal from background noise produced by other particles. Such unrealistic experimental proposals seem to condemn gravitons to remain purely hypothetical forever. And as I already mentioned, some scientists argue that gravity may not be quantizable at all. Still, scientists are trying to design experiments in which, even if it won't be possible to detect gravitons directly, it may at least be possible to create conditions where they could somehow reveal their effects. And the results of such experiments were published relatively recently. There, scientists took a thin semiconductor plate, cooled it almost to absolute zero, and exposed it to a powerful magnetic field about 100,000 times stronger than Earth's magnetic field. When exposed to the magnetic field, the electrons in the cooled semiconductor move and behave in a specific way. The experiment contains many complex details, but the key point is that these electrons behaved as expected under the assumption of the existence of gravitons. Of course, this does not directly prove their existence, but it is an interesting step toward experimental evidence for the quantum nature of gravity. Of course, this is not the only approach. There are others as well, for example those that try to use quantum entanglement effects and more. If we go back to theoretical approaches, in string theory, all particles are essentially one-dimensional vibrating strings. And in string theory, gravitons are also such strings. And in the theory, it works quite well. The main problem here is that, once again, any experimental confirmation of string theory, in any of its versions, is still very far away. And it's not even certain that it is possible at all. Another attempt to quantize gravity, loop quantum gravity, which I mentioned earlier, takes a different approach. In that picture, the key idea is not gravitons at all, but rather that the fabric of space-time itself is made of tiny discrete pieces, these so-called loops. In other words, what we are used to calling empty space in everyday life is, at the smallest scales, made up of discrete parts. One of the key properties of gravitons is that they are massless. However, even this point is sometimes debated. There are also so-called massive gravity theories in which gravitons have a non-zero mass. And there is also a more exotic idea called bigravity, where the question is, what if the gravitational field is not just one field but two? In that case, fluctuations in one field correspond to the usual massless gravitons, while fluctuations in the second field would behave like particles with a non-zero mass. Thus, this is sometimes also used as an attempt to address the dark matter problem. The idea is that maybe the behavior of galaxies and galaxy clusters is not explained by hidden mass, but rather by the fact that gravity is, in a sense, double, and that one form of gravity dominates at certain scales while another dominates at different scales. This resembles Mond theories, modified Newton dynamics, which I discussed in my video about alternatives to dark matter. But so far, we still cannot definitively say whether gravity has a quantum nature or not. It has quite a few differences from the other forces. However, if scientists manage to confirm the existence of the graviton, it would undoubtedly be a revolutionary discovery, and a major step toward solving the mysteries of black holes, the origin of the universe, and building a theory of everything. Thanks for watching. Links to all of the sources are, as always, down below in the description, and if you enjoyed the video, leave a like, comment, and subscribe for more videos in future. Bye!